C13 differential equations. I would like to talk in general about differential equations so that terminology is clear as we proceed into our course. So the first thing I'm going to do is give a definition of a differential equation. A differential equation is one that has a derivative. And a derivative, dy dx. So two very simple differential equations would be y prime is equal to x, y prime is equal to y. Let's consider this first one. We can write this as dy dx is x, and that's going to let us write dy is x dx. And then if we integrate over here, we'll have y, and then this will give us x squared over 2 plus a constant. Now the constant is usually determined in physics by an initial condition or a boundary condition. For example, suppose we know y is 0, and say in this case the y is 0 could be anything, say it's given, then that would be what c is, because when you put in 0 for x, you get y is equal to c when x is 0, so that would be c. And then we could then determine what c is. Now we consider this one solution, even though c can take on many values, but we consider one solution for one given problem which has a specific value y of 0. But before we go on, often in physics, we have an equation where, say, y is the x and x is the t, time. So in that case, you would have, say, x as a function of time, and then when t is equal to 0, that's analogous here to the case we looked at with the 0 case, that would be the initial condition, since it's when the time starts, t is equal to 0. Let's look at this next equation, y prime is equal to y, and we already have considered this, and we know the solution is going to be y is some a e to the x, because if you take the derivative, you get the same thing. But let's say we didn't know that. We would then write down dy dx is equal to y, and then we would have here 1 over y dy is equal to dx. Separate the variables. And then we integrate here. We would get, for the left side, the natural log of y. And on the right side, we would just get x. And then we went to add a constant plus c. So we could exponentiate both sides. In other words, we're going to put like an e here and an e there. And then e to the log of y basically undoes the log of y. You just simply get y. And then over here you would have e to the x plus c, which we can write as e to the x and e to the c. And e to the constant c would be our a, and we have our solution. And this value would be found by the boundary condition, or say put the 0 in for x, then you would have e to the 0, which would be 1, and you would just have a. Now let's look at the definition for an ordinary differential equation. So this would be a differential equation that has no partial derivatives. Now, so far we haven't looked at that, so the equations we have looked at are ordinary ones. They simply involve, say, a y and an x. So you have a y, say, as a function of x. And in that case, if we draw a little graph here of y and x, the derivative is going to be the slope. The derivative would be your slope. Say a rise, delta y over a run, that would be your slope as delta x goes to 0. So dy dx we can think of as, say, slope. And then we solve the equations like having the slope function, and then we integrate to find what the y is. But see, if you have a case where there's more than one variable, like say here, say x goes this way, and say this is on the ground, and say on the ground y goes that way, and then the height is z, then you can look at the slope in the x direction, and there's a slope in the y direction, which would be different. So by looking at the slope in the x direction, you would keep the y constant. Let's say, make it more look perpendicular here. And this is coming out, z is coming out of the page. So really sticking out of the page. And then you would write, for example, the slope along the x direction. This would be the derivative of the z function as the partial of z with respect to x. That would be here. And it looks like this is sloping down with the landscape. And this direction here would be the derivative partial, where you keep the x constant and you go in the y direction. Looks like that'd be sloping down too. And then you can consider, for example, the general change in the height as the partial of z with respect to x, taking the step in the x direction, and adding the contribution, the partial of z with respect to y dy. And that would be like looking at some like slant here coming out where there's a dx and a dy, then you come out there. We're not going to be doing that at this point. We're going to just focus on the ordinary differential equation. And next would be the order of the differential equation. And we're looking at ordinary differential equations here, no partial derivatives. The order would be the highest derivative. So if the highest derivative is the first derivative, it'd be a first order differential equation. If the highest order is the second derivative, it would be a second order differential equation. Now, with the first order differential equation, which we already considered two of them above here, we found one solution in each case. I would like to show you for a second order differential equation, you get two solutions. Let's take the differential equation y double prime, the second derivative, brings back the same function. Now there are two solutions we can write down here. Like the first solution would be a e to the x. That would work because when you take one derivative, you get the same thing back. But now a second one that we can consider is one where there's a minus sign in front of the x. And let me show you that both of these would work since we're taking a second derivative. So the first derivative, you would have here for dy1 dx, you would simply have a e to the x, same thing. Now for the derivative of this second one, you would have a minus sign in front because of the minus x up there. Think of the chain rule. What's the derivative of e to the minus x? You can think of that as, say, e to the u. That's going to get you e to the u. But then if you want the derivative with respect to x, use chain rule. So you're going to have in there a du dx. And since the u is a minus x, you'll get a minus 1. So this is going to be minus b e to the minus x. But when you take the second derivative here, this one would simply bring the same thing back again. But the second derivative on the second function here would bring another minus 1 down. So you would get b e to the minus x. So the second derivative, you get the same function, and they're your two solutions of the second order differential equation. Y, second derivative of y with respect to x is equal to y. Next, I'd like to mention the linear differential equation. Now, a linear differential equation is one where the coefficients in front of y prime, the derivatives, you can think of y as being no derivative or the zeroth derivative, but the coefficients are going to be functions of the independent variable x rather than y. So if, for example, with the first order, we can give an example here. If we have, say, some function of x, a1 of x, and we have y prime, and then for the zeroth derivative, right, no derivative, we have the function a naught of x, and that's equal to some function of x. You see everything here in front of the y, in front of the y prime, are functions of x. And then if we went ahead with the second order, we would have, and we'll use a sub 2 here, that function, and that's the second derivative, and then we would have an a1 of x for the first derivative, and an a naught of x for the no derivative, and then we would have, say, some function of x out here, capital F, all right? So once again, a function of x in front of the y, a function of x in front of the y prime, function of x in front of the y double prime. Now, one more term, homogeneous. Now, for homogeneous, the f function on the right is going to be 0. So if this is a 0 on the right here, then we get a homogeneous linear differential equation. And we're going to restrict ourselves to those for the rest of this discussion. They're very important in physics and in our course. A big equation in our course is going to be a homogeneous differential equation, which is actually going to be a second order partial differential equation. So now our function y double prime equals y is a linear differential equation, because what you see in front of the y double prime and the y, there's no functions of y. So you can think of this in the form that we looked at here. We could say you have a 2 of x times y double prime plus an a1 of x. This is the general formula I gave you, plus an a0 of x times the y. And over here, since we're looking at a homogeneous, the rest of this lecture here, put a 0 there. So this one here you could write down as y double prime minus y equals 0. That's what this could be written as. And that would mean that the a2, say, is a 1. And the a1 here would be a 0, since there is no y prime term. And the a0 term here would be the minus 1. A minus 1, that's in front of the y. Now, a wonderful thing happens when we have a linear differential equation. If we look at this one here, we know that the solutions here, we can write one solution as a e to the x, and the other solution as b e to the minus x. And the very, very nice thing that happens is that we can look at a linear combination of these two. Let's say a e to the x plus b e to the minus x. And that's also going to be a solution. And I would like to demonstrate this. You might say, big deal, we already know this. No, it is a big deal, and I want to emphasize that it's a big deal. So if you take the sum of here, if you go with the first derivative on this, you would get a e to the x minus b to the minus x. I know you already know this, but I want to really emphasize this because it's very important. And then the second derivative is a e to the x plus b e to the minus x. And this is y. And that's our differential equation. So that's the solution. Now, this is very, very important because our equations that we're going to be looking at are going to be linear differential equations where we can simply get the general solution by adding up the two specific solutions like this. I'd like to show you a very simple case where you have a nonlinear differential equation. It's not linear, and that would be, say, y double prime is equal to y squared. Now, if this is the case, you can't do this trick. Now, let me show you why. Suppose we have two solutions, and we know them. One solution is y1 and y2. Actually, you don't need to know specifically what they are. We just say that there are two solutions. All right, now if that's the case, then what I would like to do is show you that simply adding y1 and y2, this y, the sum, is not a solution. All right. So if we were to look at this, in this case, we would say, well, let's take the second derivative. So y2 derivatives would give you y1 second derivative plus y2 second derivative. And since these are individual solutions, we could say that this one here, y1 double prime, is going to be y1 squared. That's y1 squared. And the y2 double prime, since that is a solution, would be y2 squared. But see, this is not equal to y squared, because see, that would be y1 plus y2, that quantity squared, and you would have y1 squared plus this term that's going to mess you up, this cross term in the middle. So you say, well, I got this one and I got this one, but this is messing me up. I'm not getting this one. So that's the problem, see. this is a non-linear differential equation because the y is squared. And that term here will make it so that you cannot add the two functions together and consider it a solution. I mean, if you wanted to consider this with our rule, you would say, well, you have one derivative minus y squared, and you could think of the y as being the 0th derivative. So I would write down here, this is the coefficient 1 in front of y double prime minus coefficient y. But see, what did we say about what's in front of these things? If what's in front of a y or any derivative, this is the 0th derivative, you have to have a function of x. And see, that's a y. That is supposed to be just the independent variable, and we have the y, the dependent variable. So this would fail our test, and sure enough, we can see that the sum is not a solution. So in the text, I show you the more general case for the second order differential equation that is linear, and I show you that adding the two solutions will work. And you just have to remember here that as long as the coefficients in the front are functions of x, you have a linear differential equation, and you can combine the two solutions to get the general solution. Now, before I leave this section, I want to point out the concept of having a differential equation where there are two families of solutions. So I'm going to look at here, second order differential equation, and I want to look at a family of solutions. Now, to give you an example of what I mean by that, say y double prime is plus y double prime plus, say, some n squared of y equals 0, where n is equal to, we could say, some kind of, integer, all right? Say it's equal to 0, 1, 2, 3. So this is going to be something we encounter in our course later. So we have a differential equation, second order, where there's a family of differential equations. Since the n, there are many of them. So if you look at this equation, you're looking at, say, the second derivative is equal to minus n squared y. You get the same thing back with the minus sign, and that is reminiscent of sines and cosines. So if you have, for example, a cosine of nx, and if you have the sine of nx, if you take one derivative, this is going to become a minus n times the sine of nx, and the derivative here is going to be, you take the derivative of what's in here, say like sine of u, and you'll get cosine of u. And then when you take the derivative of the u with respect to x, you pull out that n. So this is going to be n cosine of nx. And if you take the next derivative, you would turn the sine into a cosine and bring an n out. So that'd be minus n squared cosine of nx. And this would be here going from cosine to sine will bring the minus sign in. So we're going to get the two solutions. Cosine of nx and sine of nx works because you take in the second derivative, you get the same thing back with the minus n squared. So that's the same thing back with the minus n squared. And if the y is sine of x, take the second derivative, you get the same thing back with the minus n squared in the front. So the general solution for this, and this is a linear differential equation, since what's in front of the y double prime of the y are, well, actually constants. So as long as there's no y's in front, we're in good shape. All right, so here you can consider the general solution here. Y sub n would be equal to a sub n, say cosine of nx, plus bn times the sine of nx. So you have two families. You can say this is a solution of the first kind, the cosine, and this is a solution of the second kind, the sine. Later we'll be using terminology like that when we look at the Legendre differential equation. But notice that there's one for each of the ends. So in physics applications, what's useful in physics is to find a general, super general solution for an application by doing a sum from n going from 0, all the n's, to infinity of the y and n. And actually, we could put here, introduce another constant, a c sub n, in front. So you take all these and throw another constant in front and do some kind of sum there. Since this constant can be merged with that constant there, it's just one constant in front of each, but I want to just show you that, the principle. The principle is here going from 0 to infinity, just to emphasize c sub n, y sub n of x. And that's important in physics. We would solve for the constants with some boundary condition. There's a similar situation in quantum mechanics where you solve the Schrödinger equation, which is a second order linear differential equation, and you get energies, discrete energies and solutions, which should be like the y sub n's. And then you find a super general, like a general solution by taking a sum of those with constant in front. And this constant is a measure of the probability that we would find this particle in one of those energy states. So that helps give us, this helps to give us a framework to help us understand what we will encounter later in our course.